Okay, welcome to the Wednesday session. Our first speaker today is Clarke, who is going to tell us about 3 approaches to lenses over a base.
All right, thank you very much. And thank you to the organisers for putting this all together. It's been wonderful so far. And thank you to the scientific committee for allowing me to speak here today. It's a real pleasure. So I'll be talking to you about 3 approaches to lenses over a base. And to start off, I want to give some motivation of what the talk's about, and then give a quick overview, and then we'll jump into the talk. So often in category theory, what we want to do is consider functors, but with additional properties of some kind. So for instance, we might like to consider functors which have the property of being in op vibration, so they have enough op Cartesian lifts associated to them. Now, it's possible to choose these op Cartesian lifts to get a cloven vibration. And if this choice of op Cartesian lifts is particularly nice, this extra structure is called a splitting, and we get what's called a split op vibration. Now, this path from a functor adding some property and then adding some unique structure didn't necessarily have to go this way. We could have chosen a different path. And so what we could have done instead is first start with our functor, add some additional structure which describes this splitting-like thing, and then ask that this extra structure have the property of being a split op vibration. And so if we do this kind of factorization, we get what's called a lens. Now, lenses are things that come up in the context of computer science. They're used to sort of talk about synchronization between systems. But the goal for today is not to talk about applications, but merely to talk about this really nice relationship that lenses and split op vibrations share with each other. Okay. So because every split op vibration is just a lens with a certain property, okay? And this process of considering things where we'd have property and structure and then just forgetting the property is a common theme in category theory. Like we start with Cartesian monoidal categories and then just consider monoidal categories. And so we're doing something similar here. And so what I want to tell you is actually 3 separate approaches to lenses. And so why do I want to tell you about this and why these 3 approaches? Well, in category theory, there's actually many different approaches to split op vibrations. And so because every split op vibration is a lens, it's natural to ask, well, do these approaches also generalize to the case of lenses? And so first off, I want to tell you about a FIBRED approach to lenses. So just like every split op vibration, it's in the name that they're vibrations of some kind, has a FIBRED approach. We'll also see that lenses can be seen as some kind of FIBRED notion, and don't worry about too much about the notation in this box. I'll explain it all later in the talk. Secondly, we can also see split op vibrations as algebras for some monad on functors on this category of slice, category of cat. And so also for lenses, we'll see that lenses are algebras for some monad on this slice of cat. And then thirdly, we'll see that unlike split op vibrations now, there's also some kind of co-algebraic approach to lenses where they're co-monadic over some category of co-functors. And so we'll get to that in the third part of the talk. And so each of these parts is relatively self-contained. So if you get lost in one part, feel free to come back for the next part. And so we'll get started. But before we can get started with the actual approaches, I should first tell you what is a lens. Now, so a lens is informally a functor, and it's equipped with some extra structure, which is this suitable choice of lifts. Now, what do we mean by this? Well, if we have, say, a functor from A to B, and we have some object in A and some morphism U as depicted, a choice of lift is going to be a morphism in A, like so, which lies above the morphism U with respect to the functor. Okay, and so a lens is a functor with a suitable choice of all of these lifts, and by suitable, what I mean is that these choice of lifts respect identities and they respect composition in a strict way. Okay. And so now we can define what a split op vibration is, but really this is a theorem or a proposition, is that a split op vibration is a lens whose chosen lifts are all of Cartesian. Okay, and so we can see here that a lens is some suitable relaxing of a split op vibration where we don't require necessarily that our lifts be of Cartesian. Okay, and so this definition of a lens is perfectly suitable. We can do some things with it, but when we get into trying to really show some proofs about lenses and what we want to do here today, it becomes a bit difficult to work with. And so luckily, what we have is this other characterization of lenses, which says that Well, a lens from A to B with a functor part F and a choice of list phi is actually equivalent to some commutative diagram of functors, like so. And so here F is the functor part of our lens, and here we have a span of functors where phi is a bijective on objects functor and phi bar is a discrete op vibration. And so this is actually an equivalent formulation of what a lens is. And so if you see this for the first time, you might wonder, well, how does this proposition, how are these two things the same? And so the general idea to take away is that this category X is some wide subcategory of A on the chosen lifts. Okay, so and so when we compose this wide subcategory with F, we get a discrete op vibration, which gives us our lifts. Okay, so that's what a lens is, and so this proposition will be very important throughout the later stages of our talk. So do remember this little picture. Okay, so that's what lenses are, and I want to tell you about characterizing categories of lenses. So I should tell you what the categories are. And so what we have is that for each small category B, there is some category which I'm calling lens of B, whose objects are lenses into B, like we just saw before, and whose morphisms are given by commutative diagrams of this form. So the morphisms are a pair of functors in orange, making everything commute. Okay, so we can see these little triangles here, which represent our lenses, and the orange goes between those triangles. And so more explicitly, we can just think of these as functors from A to C, which commute with the functor parts and which preserve this additional structure on our functor. They preserve the chosen lifts. Okay, so that's the category of interest. And what this does is it actually defines a functor from cat op to cat. So these categories work nice with respect to re-indexing along functors via pullback. So that's nice to know. We won't use this in the talk really. But more critically, which is something we will use in the talk, is that there are forgetful functors. Okay, so every functor, every lens is a functor with additional structure, and so we can forget this additional structure to get a functor in cat over B. And we can actually see very nicely how this works. If we look at our diagram on the left-hand side, if we apply the forgetful functor, we get this little morphism in cat over B. Okay, but now we also have another forgetful functor, which takes a lens and forgets the functor part of the lens and just remembers all this additional structure, which is choosing our lifts. And again, we can see this very nicely from looking at our morphism diagram here. If we apply the forgetful functor, we just forget the functors and we've got left with what remains here in this commuting diagram. So, and these two forgetful functors are what we'll be discussing in the second and third parts of the talk. And then finally, we have full subcategories of lens B, which are the category of discrete op vibrations, which is actually a co-reflective subcategory, and also a full subcategory of split op vibrations in the category of lens B. Okay, and so this is why we're interested in lenses, because somehow they're generalizing discrete op vibrations and split op vibrations in this nice way. Okay, so now we want to start with the first of our three approaches, which is this FIBRED approach to lens. And so what do I mean by this? Well, many kinds of morphisms, particularly kinds of functors, can be understood what we call fiber-wise. And so perhaps the best known is split op vibrations, which are equivalent to strict functors from some category B into cat. Okay, and so going from a functor into cat back to a split op vibration is this Grothendieck construction, which is very well known. A more special case is that functors from B into set are equivalent to discrete op vibrations. And then perhaps more generally, actually every functor can be understood in a fiber-wise way by looking at sort of lax double functors into the double category of spans. Okay, and so if you haven't seen this before, you don't need to worry too much about it. It's just another way of seeing functors as a fiber-wise approach. And something that's known is that it's very clear that the first and the second of these are related to each other. And likewise, the second and the third approaches are quite related to each other. But perhaps the first and the third, it's a bit less clear how we see the relationship between those. Given that every split op vibration has an underlying functor, it's not clear how we go from one of these to one of these. And actually, we'll see how this works in the next slide. Okay, so given that we see these examples of lenses as some kind of fiber-wise approach, it's natural to ask, well, can we also find the double category D, which classifies lenses in a similar way. Okay, is there a double category D such that lax double functors into it are equivalent to lenses over that category? And so because lenses are functors with extra structure, you might think of adding extra structure to the double category of spans. And that's what we can do. Okay, so what we can do is consider this double category, which I'm calling S-mult, which is the double category of sets, functions, and what I'm calling split multi-valued functions. Okay, now I don't think this double category has been seen before in the literature or has been studied much, but a split multi-valued function is just a diagram like this in set, which is just a span where the left leg of the span has a chosen section. Okay, so this is the splitting of the split multi-valued function. Okay, very good. And so this double category actually has some nice relationships with some other double categories, namely that there's identity on objects and identity on vertical arrows, double functors. Okay, so we have this forgetful functor from S-mult into the double category of spans, which just forgets this chosen section. And we also have this nice adjunction of double categories between S-mult and the double category of squares of set. Okay, so this takes every split multi-value function and composes the section with the right leg to get us a function. And likewise, every function can be seen as a split multi-value function where this part is the identity. Okay, and this adjunction will be very important on the next slide. So remember it, it's going to have a co-unit epsilon. Okay, so that's our double category. And the theorem is that we have this equivalence between lens of B and lax double functors from this horizontal double category of induced by B into S-mult. Okay, and how are we going to see that this theorem is at least kind of feasible without showing you all the details? Well, the idea is this. Given a lax double functor into S-mult, how do we get a lens? Well, we can choose our functor F like we have down here in orange, and we can take this comma category construction in the appropriate place, and if we do that, we get this projection from this integral of F, this comma category, back down to B. And actually, this is just going to be a functor. Okay, so we can do that much, but this is just giving us a functor, and a lens is a functor with extra structure. So how do we get the extra structure? Well, if we whisker F with the co-unit of the adjunction between S-mult and Q set, we'll get a lax transformation of double categories, of lax functors rather. And using the universal property of our comma construction, what this will give us is a discrete fibration, and then this universally induced functor from this composite into our comma category of interest. And so this little triangle that comes out is precisely our lenses that we get from our lax double functor. Okay, so it's really nice. It just comes out very formally from the theory once we set up our double category in the appropriate way. Good. And so once we get to this stage, we might wonder, well, split-off fibrations are special cases of lenses. And so how can we see split-off fibrations from this point of view? What we have is this condition, which says that split-off fibrations are lax functors of this kind, such that this pasting of cells in our double category S-mult is an isocell for all morphisms U. Okay, and if you see this, you might think, oh, well, this is very complicated, but it's actually just made up of very simple components, which is our co-unit for our adjunction that I told you about on the previous slide, and the lax composition constraint of our lax double functor for F. Okay, so we just paste these things together, and if we ask that all of these are isocells, we get a split-off fibration. What this is really saying is that every morphism in our domain of our lens factors uniquely into a chosen lift followed by a vertical morphism. Okay, so that's the FIBRED approach to lens. Now I want to tell you about something completely different, which is an algebraic approach to lens. And actually, it's not so different, it's related. Again, we can see that examples of lenses can be seen as morphisms with additional algebraic structure. And so what I mean by that is that, for instance, the category of split-off fibrations over B is monadic on the category of, on this slice category of cat. And likewise, discrete-off fibrations are monadic on this slice category of set. And so each of these are morphisms with additional structure. And so why do we want to consider these approaches at all, even for these cases? Well, it's useful because it allows us to consider generalizations of these concepts in other categories. So for instance, we can replace cat with any two category with pullbacks and comma objects, and we can use this to describe split-off vibrations in any two category we like rather than just cat. And likewise, we can describe internal discrete off vibrations in any category with pullbacks when we replace this with set. Okay, so what this tells us is that we can consider these concepts in other contexts, and we might wonder, well, can we also do that for lenses? Are lenses algebras for a monad? And so back in 2013, there was this result which says that, well, actually lenses are certain algebras for a semi-monad, so a monad without a unit. And so this is what it is. It's not really important what it is, but if you see this result, you might feel a little bit unsatisfied because we see these other kinds of lenses as algebras, and we might wonder, well, can we actually improve this result? Can we actually show that this forgetful functor from lenses to functors is monadic? And it turns out that we can, and we'll show this on the next slide. But actually, this has a further use, which is if we can show this, can we also use it to generalize lenses to other contexts by replacing cat with something else? Okay, so how do we want to show this result? Well, first of all, recall that cat has an idempotent comonad on it, which takes every category to its discrete category. And it also has an orthogonal factorization system, which factors every functor into an initial functor followed by a discrete off vibration. This is the comprehensive factorization. And using these two facts that we recall, we can actually prove our theorem. Well, not prove our theorem, but we can at least show very easily what the left adjoint for this monadic functor is going to be. And so let me step through it. The idea is this: if we have a functor from A to B in orange, and we precompose it now with the co-unit of our idempotent comonad, this inclusion of our discrete category, it's a bijective and objects functor, and we use this little squiggle to denote that. Now, if we take the composite of this and factorize it using our orthogonal factorization system, what we get is this initial followed by a discrete op vibration. And then third step is that we can push out this cospan here. Now, bijective and objects functors are stable under push out, and what we end up getting is this little triangle which represents our lens. Okay, and so that's how we take a functor and get a lens. Now, why is this result useful? What's the payoff? Well, actually, we get this really nice corollary, which says that because we have these two adjunctions now of lens being split off vibrations over B on this slice category, using our adjoint triangle theorem, we can actually show that there is a left adjoint to the inclusion of split off vibrations into lenses. Okay, which is really nice because it means that we can take these lenses, which are just structure, and universally turn them into split off vibrations, which are a lot nicer things to work with. And it means every lens can factorize into a split off vibration and so on. So there's lots of really nice things, and actually showing this left adjoint explicitly is a very difficult task. And here we just see it come out very nicely from some category theory. And a bonus is that we can actually use this result to generalize. So we can replace cat with any category together with an idempotent comonad and an orthogonal factorization system together with some properties, and we can use this to generalize this monad. I don't have time to go through this example, but ask me at the end if you're interested. And so finally, I want to tell you about the co-algebraic approach to lenses. And again, this has close ties with the algebraic approach, as we'll see. And so what's it co-algebraic over? Well, it's co-algebraic over this category cof of B. This category has objects which are cofunctors. And cofunctors may be unfamiliar, but they're very easily described as just spans of functors, which one leg is a bijective and objects and the other leg is a discrete off vibration. So there's something a bit weaker than a lens. And so the objects are cofunctors, and the morphisms in this category are just what you would expect, I suppose. They're just pairs of functors which make these things commute. Okay, and so the third part of our talk is we want to show that this functor is comonadic, and also maybe see if this also gives us a generalization of lenses. And so one thing we can note, first of all, is that lens of B is actually equivalent to the slice of cofunctors over B, sliced over this trivial cofunctor, the identity. Okay, so if we look at a morphism here, we actually see that this square is just a triangle, which is a lens. Now, from this lemma, we can actually just prove comonadicity very easily, because it's just a forgetful functor from a slice to cof, but we can actually see it a little bit more concretely. So again, recall that CAT has now an idempotent monad, which takes every category to its corresponding co-discrete category on the same set of objects. So notice the similarities between this and the algebraic approach we saw before. And we can use this to prove our theorem that lens B is comonadic over conv B. And here's the idea. Again, we start with our cofunctor, which is this span of functors. And we can complete this to a commuting square using the unit for our monad. So everything goes into a co-discrete category. And again, having this diagram, we can now pull back rather than push out like we saw before. And again, using just properties of our functors, we see that this little triangle here gives us our lens. So this is describing the right adjoint for this comonadic functor. Cool. And so there's this open question whether split-off fibrations is actually comonadic over cofunctors as well. And again, we can use this to generalize this comonad by replacing cat with any category together with an idempotent monad and some class of morphisms. Cool. And so just to summarize, here we saw three separate approaches to lenses, a fibered, an algebraic, and a co-algebraic approach, and we saw how these were related to split-off fibrations. And so this is really nice for our applications in computer science, but it's also really nice for giving us new ways of understanding split-off fibrations, and it also inspires a bunch of future work. And so if you're interested in any of this, please get in touch, and here's my website where you can contact me. So thank you very much.
So, are there any questions?
Thank you. Hi, Bryce. Thank you for your talk. I haven't thought about these things in a while, but if I understand well, the lenses you're talking about are asymmetric lenses, right?
Yes, that's right.
So have you used your work and all those nice descriptions in the symmetric lens case, which is the one that's mostly used in applications, if I understand well?
Yes, so there are some links with symmetric lenses, which I didn't have time to go into detail here today, but we can actually use these lens B categories to construct our categories of symmetric lenses. So we can make a bicategory of symmetric lenses, and the Holm categories of this bicategory can actually be constructed from our lens B categories in a suitable way. So yes, so there are links with symmetric lenses, and I hope to look into them further in the future, but yes, that's all I can say at the moment. So thank you for your question.
Any more questions from the audience, or anyone with a hand up on Zoom?
Hi, Bryce. Thanks for a really nice talk.
Thanks, so.
I was just wondering if you've looked at all at some sort of enriched approach to lenses.
Yes. So there is an enriched approach to lenses, which is quite different to what we've seen here today. But yes, this is ongoing work with another colleague of mine, Matt Demeglio, who will give a talk tomorrow, not about enriched lenses, but yes, there is work on enriched lenses, and hopefully I get to talk about that sometime in the future.
There are no more questions. Let's thank Bryce once again. And we have 5 minutes before the next